Hey everyone, and welcome to Crack Civil with AI. If you're gearing up for exams like the TNPSC AE, SSC JE, or GATE, you know there are some concepts you just have to get right. Today, we're diving deep into one of the most common points of confusion: centroid versus center of gravity. Trust me, get this right and you're building a rock-solid foundation for pretty much all of strength of materials. So let's just jump right in. Centroid, center of gravity. We hear these terms thrown around all the time, sometimes like they're the same thing. But are they? The answer is a huge, definite no. And understanding why they're different is absolutely critical. So let's spend the next few minutes making this crystal clear. You know, the entire difference between these two ideas, it really just boils down to one simple question. Are we talking about a real physical object that you can actually hold in your hand? Or are we talking about a flat shape, something you draw on a piece of paper? One is all about physics and gravity, and the other, it's about pure geometry. Okay, check this out. This breaks it down perfectly. On one side, you've got the center of gravity, or CG. This is for real-world 3D objects, things with volume, right? A cube, a sphere, a beam. Because they have volume, they can have mass. And where there's mass, gravity creates weight. So the center of gravity is that one special point where we can imagine all of that weight is concentrated. But on the other side, we have the centroid. This is strictly for 2D figures. A simple rectangle, a triangle, a circle on a page. These things only have an area. They have no volume, which means no mass and definitely no weight. Let's just walk through the logic step by step so it really sinks in. Imagine a solid steel cube, maybe 1 meter by 1 meter. Okay, first step, it's a 3D object. Simple enough. Because it's 3D, it has volume. That volume has mass, a lot of it actually, around 7,850 kilos for steel. And then gravity pulls on that mass, which gives it weight. The center of gravity is just the geometric center of that cube, the single point where we can say all that weight is acting. It's a chain of logic. 3D leads to volume, volume to mass, and mass to weight. So, if you're going to burn one thing into your brain from this, let it be this definition right here. The center of gravity is the point where the entire weight of a body acts. The key word, the only word you really need to focus on, is weight. Got it? Good. All right, that all makes perfect sense for a solid 3D object. But what happens when we shift gears? What if we're just looking at a simple rectangle drawn on a sheet of paper? Can we still talk about a center of gravity? Does that term even make sense anymore? And the answer, of course, is no, we can't. Think about it. That rectangle on the paper has an area, for sure, but its thickness is basically 0, right? So its volume is 0. And if the volume is 0, well, its mass has to be 0. And if mass is 0, its weight is 0. There's no weight for gravity to act on. So that whole term, center of gravity, becomes totally meaningless. We need a different name for this. And that new term, that's the centroid. It's the perfect 2D equivalent. So instead of being the point where all the weight acts, the centroid is the point where the entire area of the figure is assumed to act. See the difference? It has nothing to do with physics or gravity. It's pure, simple geometry. Okay, I get it. The idea of an area acting at a single point can sound a little weird and abstract. So let's use a really powerful analogy to make this concept feel totally intuitive. Think about it. When you look at a map of India, you see this huge, massive area. But if you want to find a city, what do you look for? You don't look for its detailed boundary, right? You look for a single dot. This very simple question is the key to understanding what a centroid really is. Exactly. That little dot on the map for, say, Nagpur or Trichy, that's its representative point. And it's not just some random dot. It's placed right at the geometric center, the point that best represents the location of that whole area. That dot is the city's centroid, and that's all a centroid is for any shape. It's just its best, most central representative point. So why are we spending so much time on this? Is it just a fun geometry puzzle? Absolutely not. For you guys, for your exams, understanding the centroid is non-negotiable. I mean it. You literally cannot solve some of the most fundamental engineering problems without it. And here it is, the big connection. In strength of materials, when you're analyzing how a beam bends when you put a load on it, you have to find something called the neutral axis. This is the line inside the beam's cross-section where there's 0 stress. And guess what? For simple bending, the neutral axis passes exactly through the centroid of that cross-section. So if you can't find the centroid, you're stuck. You can't solve the bending problem. This is a must-know for your syllabus. Super important. Now for my favorite part. Calculating centroids for really complex shapes can mean doing some pretty heavy math, but for a ton of shapes you'll see in your exams, there is a massive shortcut, a trick that will save you an incredible amount of time. Okay, listen up. Exam trick here. You must note this down. This is the golden rule, the one you can't forget. If a shape has an axis of symmetry, a line where you could fold it and it matches up perfectly, then the centroid has to lie somewhere on that line. It's a geometric fact, no exceptions. And using this rule is so simple. Step 1. Just look at the shape and find any axes of symmetry. Step 2, if you only find one, great, you know the centroid is on that line somewhere. But step 3, this is the real game changer. If you find 2 or more axes of symmetry, boom, game over. The centroid is exactly where they cross. No formulas, no calculations, you're done. Okay, let's put this amazing trick to the test. We'll do a little rapid-fire round with some shapes you'll see all the time. Watch how fast this is. A rectangle, it has 2 axes of symmetry, horizontal and vertical. Centroids at the intersection. Done. A circle, it has infinite axes of symmetry through its center, so the centroid is at the center. Done. An isosceles triangle, just one vertical axis, so we know the centroid is on that line. But a Z-section, no axes of symmetry. And just like that, that's the one where you've got to break out the formulas and do the actual calculation. So let's do one final recap to lock this into your memory. Center of gravity, that's for 3D things. It's about mass and weight. It's a physical point. Centroid, that's for 2D shapes. It's all about area. It's a geometrical point. Simple as that. So, using that symmetry trick is a fantastic shortcut for simple shapes. But what happens when the exam throws you a composite shape, like a T-section or an I-section? How do you find the centroid then when you actually need to use the formulas? Well, that's the next big step in mastering this topic. If this helps clear things up for you, make sure you hit that like button and definitely subscribe to Crack Civil with AI so you don't miss our next explainer. If you have any questions, drop them in the comments below and share this with your friends. Keep up the hard work.